morning, students. Today's class, I'm going to discuss Smithchart. Okay. So Smithchart is basically a unit circle which consists of two circles. One is normalized resistance circle, second one is normalized reactance circle. Okay, Smithchart is basically superimposition of normalized resistance circle and normalized reactance circle. So these full circles are called as normalized resistance circles, and the half circles are called as normalized reactance circles. Okay, this is Smithchart. So this is for inductive reactance. It indicates inductive reactance, and this indicates capacitive reactance. Okay, so since we are drawing the circles using the normalized resistance and reactance, this Smithchart is also called as normalized Smithchart. Okay, so we should remember some of the important points regarding the Smithchart. So this point is called as POC, nothing but open circuit point. So at this point, what is the impedance? It is infinity plus J infinity. Resistance is infinity and impedance is infinity. Okay, and this point is called as PSC. So for short circuit point, what is the impedance? 0 plus J0. Okay, this is the first point. Coming to the second point. Okay. Coming to the second point, the distance between PSC and POC. So to identify that, so take some waveform here. I am taking one sinusoidal waveform. This is of length how much? Lambda by, this is the lambda, right? Wavelength. So this gives half of the wavelength, lambda by 2, and this is going to give the quarter wavelength, lambda by 4. So in this waveform, here to take it as voltage waveform, here the voltage is minimum and this is having maximum. So when the voltage is minimum, at the short circuit point, the voltage is minimum. Therefore, I can take this as a PSC point, and when it is maximum, the voltage is maximum. It is having an open circuit point. Therefore, I can take this point as a POC point. Okay. So from this waveform, what can observe? The distance between PSC and POC is lambda by 4. Okay. The distance between PSC and POC is lambda by 4. Okay, therefore this is going to give half circle value for one complete circle. For one complete circle, I can take it as lambda by 2. Lambda by 2 is equal to 360 degrees because it is one complete circle. Therefore, I can take 1 lambda is equal to 720 degrees. So, in some cases, should convert the distance in terms of degrees. In that case, I can use this value. 1 lambda is equal to 720 degrees. This is the second point should be noted. First point is location of PSC and POC, and second point is 1 lambda is equal to 720 degrees. And next point. Lambda is equal to 720 degrees. And next point, moving on transmission line is same as that of moving on constant VSWR circle. This is the load impedance. This comes under source side, and this comes under load side. Okay, and Z dot is the characteristic impedance of the line. Okay, so here the next point is from this point it is take it as some A, take it as some B, and take it as some C. Let us assume. For example, if I am moving from point A to point B, at this point, what is my input impedance? Because we know that if we move on the transmission line, the input impedance varies. So looking from this side, the load with this line is treated as input impedance. If you move from here to here, looking from this side, the load with the line act like input impedance. That means as the length of the line varies, the input impedance varies. Okay, so how to find out the input impedance at any point on the line? So for that, we have to follow some procedure. So this is a Smith chart. So outer one is pure imaginary. That means what? That means it contains only reactive inductance. The point is there here means I can take it as minus J X C. On the outer circle, it contains only purely inductive reactance, some reactance. If this point is bottom hemisphere, it contains only pure capacitive reactance. If a point is here, this contains purely inductive reactance. And this is called real axis. So here, it contains only purely resistive loads. So this is only purely resistive loads, normalized resistance. So at any point on this line, it contains only real values. At any point on the circle, it contains only imaginary values. That is the point. So this is a POC point, and this is the PSC point. So this is our Smith chart. Okay, what is our objective? Our objective is to find out the impedance at any point on the line. Okay, So first step, what have to do? We have to find out the normalized load impedance. ZL bar is called as normalized load impedance. So dividing the impedance with characteristic impedance gives the normalized value. Okay. Generally, while drawing the Smith chart, you have to find out the first point is find out the normalized load impedance and plot this point on Smith chart. So since it is complex load, so it contains some R1 plus some JX1 that I am assuming. Okay, it may be anything. It may be R1 minus JX1, anything. Based upon the value of load impedance, this point lies either here or here. So any point here is what? Any point here is purely resistance plus inductive reactance. Any point here in this half hemisphere is R minus Jx. Okay. Now, what is the step you have to follow? First step is you have to plot the normalized load impedance. So this is called ZL bar. That I am assuming that point is here. Okay. So that's nothing but what is this circle? This is a R1 circle. Similarly, you have to take a X1 circle. Let us. This is X1 circle. Okay. How to get impedance means intersection of R1 circle and X1 circle is going to give the impedance ZL bar, normalized impedance ZL bar. Okay. For any problem, this is the first step, plotting the normalized load impedance on the Smith chart and name it as some point A. Okay. So this is a point A. So at this point, the impedance is nothing but your ZL bar. So my objective is to find out what is the input impedance at a distance of some lambda by something 6 I can take. I can take any value, no problem. So simply to find out, I am taking this value. So my objective is to find out what is the impedance at a P point, normalized impedance at a P point. Okay. So the point to remember here is moving on line is same as that of moving on the constant VSWR circle. So for that, I am drawing here one constant VSWR circle. So take it as this is as O. How to draw constant VSWR circle means after plotting the normalized load impedance with the OA as radius. With the OA as radius. Draw a circle. With OA as radius, draw a circle. That circle is called as the constant VSWR circle. So this is the constant VSWR circle. Okay. So moving on the line is same as that of moving on a constant VSWR circle. Okay. Now there are two cases are there. So either I can move from source to load or I can move from load to source. So two cases may possible. If I want to find out the load, I know this B point impedance. If I want to know the impedance at A point means I have to move from source to load. Here in this case, I know the load impedance, but I want to find out the input impedance. So in that case, you have to go for load to source. Okay. So when I am moving from load to source, I should move in clockwise direction on constant VSWR circle. Okay. If I am moving from source to load, in this case, I should move in anti-clockwise direction on the constant VSW circle. This you have to remember. Okay, because if you did any mistake in this point means you may get wrong answers. So for that reason you should remember this point, whether I am moving from load to source or from source to load. So in this case we are moving from load to the source because we want to find out the input impedance at source side kabatti. Okay, so here we have to move in clockwise direction on the constant VSW circle for a distance of lambda by 6. Okay, so what is lambda value? 1 lambda is equal to 720. So lambda by 6 means 720 by 6. What's the value? So this is how much? It is 120. So from the load point we should travel a distance of 120 degrees to reach the B point. Okay, so here this is now we should take this as a reference line. Okay, now we should take this as a reference line, GOA as a reference line. So from this, use a protractor and plot 120 degrees. Then I am taking this as 60 and one more 60 means up to here. So I am taking this as 120 degrees. Okay, now move on this point DA on this constant VSW circle until it reaches 120 degrees. Okay, therefore this point is called as a B point. Okay, so at this B point I can see some X circle is passing and some R circle is passing. Note down those values. So at B point I can see some R2 circle and minus J some X2 circle. Why I am taking here minus means because it contains capacitor reactance, already we seen, right? Therefore it is R2 minus JX2. So at this point what is the impedance? I can take it as Z in bar at lambda is equal to 6 is equal to R2 minus JX2. So why I am taking here bar means because whatever the points we are getting on the Smith chart, all are normalized values. Then therefore you should write here as bar. Bar indicates it is a normalized value. Okay, therefore the input impedance at this B point is that much value. Okay, now how to find absolute value? Zn is equal to Zn bar into Z naught. It is going to give the absolute impedance at B point. So this is the third point. First point is superimposition of R and X circuit gives Smith chart, and it contains some OC point and short circuit point. I represent them, and 1 lambda is equal to 720 degrees. Moving on line is same as that of moving on constant VSW circle. So how to get the constant VSW circle? First plot the normalized load impedance on Smith chart and name it as point A with OA as radius. Draw a circle that is going to give the constant VSW circle. So from point A, travel distance of lambda by 6. How to find lambda by 6 means 1 lambda means 720. So by 6 gives 120 degrees. So from point A, move in clockwise direction from this information. Move in clockwise direction on this constant VSW circle at distance of 120 degrees. That gives B point. At B point, identified the R circle and X circle. You have to keep minus here because the bottom hemisphere is capacitive reactance. Okay, therefore this is going to give the normalized input impedance at lambda by 6. To find absolute value, normalized value into Z0 gives the absolute value. Okay, this is the procedure to find out the input impedance at some distance. Okay, and next one is okay. So with this information, I would like to explain some of the concepts, that is applications of transmission lines. So here we will discuss 3 applications. One is quarter wave transformer technique. And second one is single stub matching technique. And third one is double stub matching technique. So all are the applications of finding impedance matching. So impedance matching is very much required in the transmission lines to avoid losses. To avoid reflection losses, we have to get impedance. We have to do impedance matching for the transmission lines. So there are 3 methods are available. So it is having some drawbacks, that is overcome in single stub matching. It is also having some drawbacks that are overcome in double stub matching technique. Now we will see one by one. So first we will discuss about quarter wave transformer technique. So the name itself indicates quarter wave, that means lambda by 4. So for impedance matching purpose, I am using a transmission line of length lambda by 4. Okay, so here this is one transmission line with the characteristic impedance Z0 of some length. Okay, so this is the load impedance I can take. So what is the formula of reflection coefficient? Gamma L is equal to ZL minus Z0 by ZL plus Z0. So this is the formula of reflection coefficient. Okay, if ZL is not equal to Z0, then gamma L does not equal to 0. It has some value that indicates there is some reflection present. So fraction of the wave will be reflected back to the source side. According to the maximum of power transfer theorem, okay, if the load impedance is equal to input impedance, then the maximum power is transmitted from source to load. That is what I am expecting. Okay, but if any impedance mismatch takes place, fraction of the wave will be reflected back to the source side. That is not required for us. So by using some technique, we have to do impedance matching between the source to the load. Okay, therefore here because ZL is not equal to Z0, some wave will be reflected back. To avoid that, we have to use some device or some technique to do impedance matching. Okay. Now here we see, with the help of a quarter wave transformer, we have to do impedance matching. Okay. So this is my transmission line, and here I have to take one more transmission line of length lambda by 4. So this is called as quarter wave transformer Why the name quarter wave transformer? One of the application of transformer is impedance matching. Here with the help of this branch line of length lambda by 4, we are doing impedance matching. Hence the name quarter wave transformer technique. So here I can explain two cases. Case 1 is if load is real, that means it contains only resistive load. Case 2 is if it is impedance, that means it contains some resistance and reactance. So in both the cases, we have to analyze this quarter wave transformer technique. Okay, so it is not a box. I have taken it as a box, but it is a transmission line. It is also a transmission line. So if you take this, it looks like this. So this is also a transmission line. This is also a transmission line of length lambda by 4. So this is your transmission line with the characteristic impedance ZOX. This is also a transmission line, but of characteristic impedance Z0. So this is having the load impedance R. Okay, now we'll see how to do impedance matching with the help of this quarter wave transformer using Smith chart. Okay. So name it as some points here. This is A, this is B, and this is C. So our object is after the quarter transformer, impedance should be matched because we are using this transmission line for impedance matching purpose. Therefore, at C point, the impedance must be equal to Z0. Therefore, this is Z0 and this is Z0. Therefore, impedance matching takes place. Therefore, there is no reflected wave from here onwards to the source side. The reflection may occur only at this terminal, but after this quarter transformer, there is no reflected wave to the source side. Okay. Now, I am drawing Smith chart to explain the concept. Okay. This is impedance. This is the Smith chart, normalized Smith chart. What is the first step you have to follow? Always the first step is plot the normalized load impedance. So in this transmission line, what is the load impedance? This is R, because I am taking this for case 1 where the impedance is only real. So this is point A and this is point B and this is point C. The length of this line is how much? Always this is lambda by 4 only. Okay, what is the first step you have to do? Plot the normalized load impedance. What is this one? Z0 is the characteristic impedance of the line. Therefore, and what about this one? It is having the characteristic impedance ZOX. Okay, since load is connected to this transmission line, we should normalize this load with this characteristic impedance, not with this characteristic impedance. That should be remembered. So here the load is connected to this quarter wave transformer whose characteristic impedance is ZOX. So definitely we should normalize this load impedance or resistance with ZOX, not with Z0. Okay. So what is the value here? The impedance at this point is how much? This is R by ZOX. So where this point lies? Already we discussed this point. This contains only pure real values, and outermost circle is pure imaginary. So since this point is purely real, definitely it lies on this real axis. I am assuming that this is at this point. R is equal to A is equal to R by Z O X. And it is RL or something, anything else. Load impedance or load resistance, RL. Okay, that is the first step. So what is the next step we have to take? So from this point, I can take like this because it is connected directly here. So no need to write one more point here. So this is my load. So this is A. Okay. Since I am straight away connecting the load to this quarter transformer, I want to take another point here. This is A and this is B. Okay. So from this point, you should move a distance of lambda by 4 to reach B point. So in the previous topic, what you have discussed, moving on line is same as that of moving on constant VSW circle. So what have to do now? We have to draw a constant VSW circle. So this is with OA as radius. Draw a constant VSW circle. Okay. So from this point, how much distance we have travel? Should travel distance of lambda by 4. Okay. Already we seen, right? This is the one complete cycle. That means 1 lambda. So this is going to give lambda by 4. So this is we have taken as a short circuit point and this is an open circuit point. That means if you travel distance of lambda by 4, it is going to give the inverse point. That's the point, right? So here from point A, travel distance of lambda by 4. So this is lambda by 4 distance, right? So at this point, what is the impedance you can take? It is the inverse of impedance at A. Therefore, this gives 1 by RL by ZOX. That is equal to ZOX by RL. So this is the impedance at B point. Okay, because travel distance of lambda by 4 is going to give inverse point. There's one more point regarding the Smith chart. Travel distance of lambda by 4 on Smith chart gives inverse point. Therefore, it is going to give inverse point. Therefore, the impedance, the normalized impedance at B is equal to ZOX by RL. Okay. So what you are trying to say here? So after this quarter transformer, definitely the impedance must be matched. That means what? That means this is a normalized, right? So first of all, find out the absolute impedance at B. Absolute impedance is equal to how much? Normalized impedance into Z0. That is equal to, what's the value of ZP? ZL power B, ZOX by RL into ZOX. Here the characteristic impedance is ZOX, so we take the ZOX, it is equal to ZOX square by RL. So this is the absolute impedance at point B. So what I am trying to say here, after the quarter transformer, impedance match to occur. Therefore, this should be equal to Z0. Then only you can say that impedance matching occurred. That means I can take ZOX as root of Z0 into R. That means we should design this quarter transformer with the characteristic impedance equal to geometrical mean of Z0 and RL. Okay. Then only the impedance at B point is equal to Z0. Okay. The impedance at B point should be equal to Z0 only when we are designing a quarter transformer with the characteristic impedance ZOX equal to geometrical mean of Z0 and RL. Okay. Okay. So what is the drawback in this method? whenever the load impedance, here the ZOX term depends upon RL. So whenever load impedance varies, ZOX varies. Therefore, as the load impedance varies, we have to keep on change this quarter wave transformer with the desired ZOX. Then only impedance matching takes place. That's a drawback in this method. To overcome this drawback, we are going for a single step matching technique. Okay, before that, load is real. In case if it is complex, in that case, how to do impedance matching? That is for case 2. Okay. So here this is a quarter transformer. So what we have to do here is we have to place one more branch line of different characteristic impedance before this quarter transformer. So here you can see two transmission lines, three lines. One is your main transmission line, another one is the quarter transformer of length lambda by 4 with the characteristic impedance ZOX, and third line of some length. We don't know that length. Based upon load impedance, we have to set the location of the quarter transformer with a different characteristic impedance. So the idea here is, since it is complex, RL plus some JXL, okay, the idea is we know how to match a real load with the Z0. Therefore, we have to use one more transmission line of some length L such that after this point the impedance is some real value. So the idea here is converting this complex load to real value with the help of a third transmission line. That is only the difference. Okay, if you come and put this Smith chart here, the first point is, so let us assume this is the complex load. This is R plus JXL. What is the next step? With the OA as radius, should draw a constant VSWR circle. Okay. So have to choose this length in such a way that after this length it should give some real value. Okay. So move on this constant VSWR circle. This is nothing but this line. Okay, so that it is going to give some real value. So after moving a distance of some L suffix C on this constant VSWR circle, it is going to give real value. Now here we know. So from this R, go a distance of L suffix C lambda by 4 to reach this point B. So this is nothing but your A point, this is a B point, and this is C point. Okay, now from this this is a B point, travel distance of lambda by 4, nothing but this is the 1, it is going to give C value, it is having some impedance. This impedance should be equal to this is a normalized value, this value must be equal to the absolute value of C, that value must be equal to Z0. That is the procedure how to follow while matching a complex load with Z0. Okay, so this is all we know. How to match a real load with Z0. The one more point here is first converting a complex load to real load with the help of a third transmission line. Okay, so this length again, the location of this auto transformer varies, depends upon the load impedance. If it is here, this is the length. If this is here, this is the length. If it is here, this is the length. Okay, therefore, as the load impedance varies, you have to keep on change the location of the auto transformer for impedance matching purpose. Similarly, we also change the transmission auto transformer with different ZOSs based upon the load what we have at B point. So these are some of the drawbacks in a quarter-wave transformer technique. So you can overcome these drawbacks with the help of a single step matching technique. Now we see single step matching technique for impedance matching purpose. Second one is single stub matching. Okay, next class we'll discuss about the single stub matching technique.